Hi, in this video we are going to talk about QuickSort algorithm using Hoare's partition. We have already talked about QuickSort algorithm using Lomuto partition. We are talking them separately because our main QuickSort algorithm changes according to partition. Also, different academic environments, they teach different partitions. So let's understand QuickSort considering Hoare's partition. The idea of QuickSort is this. You have a partition algorithm which takes a pivot, divides your array elements around that pivot. So your Hoare's partition, it considers first element as a pivot. It puts all the smaller than or equal to elements on left side and all the greater than or equal to elements on right side. So your different partitions can be sorted independently and your whole array becomes sorted. Let's take this example. Using Hoare's partition, we consider 8 as a pivot. And when you call Hoare's partition, what happens? All the elements which are smaller than 8, they go to the left side, and all the elements which are greater than or equal to 8, they go to the right side. This is how your Hoare's partition your algorithm. 5, 4, 7, 3, they go on the left side. 9, 10, 8, they go on the right side. Now, if you sort these arrays independently, right? If I sort this, I'll get 3, 4, 5, 7. If I sort this, I'll get 8, 9, 10. I don't have to do anything extra after that. I just have to do the partition. And after partitioning, if I sort this independently and sort this independently, my whole array is sorted. If I sort this sub-array of my array independently and this sub-array independently, because all these small elements are smaller than or equal to all these elements. So if they are sorted and they are sorted, there is no element which is going to be moved on this side and there is no element which is going to be moved on this side. So if they are sorted independently, you are done. So in QuickSort, your main function is partition function that partitions the array around the pivot, and once the partitioning is done, you just have to recursively call left part which is smaller equal to right part which is greater than equal to. That's all your QuickSort logic is. So there is a base condition which says that there should be at least 2 elements to sort. If you have only 1 element to sort, then nothing to be done. Right? So L smaller than H means there should be at least 2 elements to sort. So when that is the case, you find the partition point by calling the partition algorithm. Then you call QuickSort from L to P, and then you call QuickSort from P plus 1 to H. So if you take a look at this array example, your L is 0, your H is 6, and this is considered as pivot by Hoare's algorithm. And after partitioning, what happens? Your left array becomes this and right array becomes this. And your Hoare's partition returns an index 3, right? Which means elements from 0 to 3 are smaller than or equal to elements from 4 to 6. That's what Hoare's partition guarantees. So what do? You get 3 as an output in the partition here. So you initially pass 0 and 6 to the partition function. And we have already talked about this partition function. If you have not seen the Hoare's partition video, it's strongly recommended that you see that video first. So what that video does, that returns 3. So P becomes 3. Now what do? We call from 0 to 3, and then we call from 4 to 6. And if we sort them independently and sort them independently, our whole array is sorted. We don't need to do anything more. So there is nothing after this line. You just have to sort these 2 sub-arrays independently. So let's do a dry run of this algorithm with this example. Let's see what all happens when you run this algorithm. So you initially pass 0 and 6 to this QuickSort function. I have written QS here, which means this QSort only, right? We have to type it again and again, so I've used the short form here. So L is 0 initially and H is 6. Now we call the Hoare's partition function, and what this function does, it modifies this array to 5, 4, 7, 3, and then 9, 10, 8. That's what this function does. And it returns you this index P. right? So you get P as 3. Now what do? After you get this P as 3, you go to this recursive call, right? And when you come to this recursive call, you call from L to P, which means you call from 0 to 3. So you call from 0 to 3, the partition function is called again in this recursive call. So let's see how does this 0, 3 call work. So when you call from 0 to 3, you again begin from here. 0 is smaller than 3. So you will come here and you will again call the partition function for 0 to 3. So you will call partition for this array. And what partition function will do? It will rearrange this array as 3, 4, 7, 5. So I'm directly writing the output of partition function everywhere because we have already talked about Hoare's partition. And your partition function will return you this index, which is 1. P is 1, right? So what will you do? After partition is over, you will call from 0 to 1, L to P, right? That's what we do here, right? So when you call from 0 to 1, you again begin execution from here with these indexes. Since L is smaller than H, you will come inside. When you come inside, you will again call partition and Hoare's partition. So Hoare's partition is called for 3 to 4. And what this partition does, it makes this array 3 to 4 only. It keeps the array as it is if you run the Hoare's partition algorithm. And it returns you pivot index as 0. This is what your new P is, right? So you call from L to P, which means 0 to 0, and then you call from P plus 1 to R, which means 1 to 1, right? So you have two calls after it, 0 to 0 and 1 to 1. So 0 to 0 call will begin from here and it will see L is equal to H now. So it will immediately return, right? So your this call returns immediately. And this call, this will also see that L is equal to H. So it will also return. So your caller gets the control back. It has done the partitioning, called QuickSort for left half, called QuickSort for the right half, right? And it is done. So it will also finish immediately. This call will also finish immediately. It will give the control back to the caller. So caller, which had done the partition, had called for the left half, and left half is now sorted. Now will call for the right half, right? Right half is 7, 5. Right? So Hoare's partition is called for this subarray. So when you call for this subarray, what happens? Your array changes from 7, 5 to 5, 7. So when you change it to 5, 7, you again call from 2 to 2 because this is a pivot, new pivot return, and 3 to 3. These two calls, they come here and they immediately finish because they have only one element, right? So they don't go inside. So once this is done, it sorts the array to 5, 7, gives the control back to the caller, and caller has now complete array sorted 3, 4, 5, 7. After doing this, your caller gives control back to the main function, this function, and this now calls this part. And this part is also going to call recursively this way and ultimately going to sort the array as 8, 9, 10. Right. Now caller has both the parts sorted 3, 4, 5, 7 in 8, 9, 10. It does not have to do anything more, and caller also finishes and your whole array is sorted. When we implemented QuickSort using Lomuto partition, we called QuickSort from L to P minus 1. This is where Hoare's partition differs from Lomuto partition. Lomuto partition ensures that the pivot is fixed at its correct position. Then it calls for the left half and right half, and it calls for left half from L to P minus 1, right? Because P is fixed, it goes to its sorted position where it should be in the sorted array. But Hoare's partition, on the other hand, does not guarantee that thing. What it does, it ensures that the element on the left side are smaller than or equal to elements on the right side, right? And it returns you index of the last element of left side. So that's what is done by Hoare's partition. It does not fix any element at its correct position. It only partitions. That is why we call the recursive QuickSort from L to P, right? Not to P minus 1 when we are using Hoare's partition. And other recursive call is same. Other recursive call is same in both Hoare's partition and Lomuto partition. Hoare's partition is much faster than Lomuto partition in general. There have been studies which say that Hoare's partition is 3 times faster than Lomuto partition on average. However, like Lomuto partition, Hoare's partition is also not stable. We did an example of an array where all the elements are same in the Hoare's partition video, and we saw that the elements were changing their positions even if they were same. That makes it unstable. There is one naive partitioning algorithm that we discussed. That's the partitioning algorithm which is stable. These two, Lomuto and Hoare, are not stable.